Okay, all right. So today's speaker is, welcome to the best seminar of the year. Today's speaker is Joanna Drazkowska. So she is an expert in planet formation, disk dynamics, and so on. And she did her PhD in 2014 from University of Heidelberg. So Keith Tillemann is her PhD advisor. He's very famous, if you know. And after that, she was a postdoc in the University of Zurich and at LMU in München. And then starting 2022, she has got an ERC grant. Yes, so right now she has her own group in MPS. So that's Max Planck Institute for Solar System Research in Göttingen. And her group is called Planetoids. So they study similar things, building blocks of planets, formation of solar system in an integral framework, from a theoretical point of view. And she has also written one of the best chapters in PB7, so chapter 20, which pertains to the formation of planets in the era of ALMA and Kepler. So Joanna, please.
Thanks a lot, Condan, for your kind introduction, and thank you a lot for inviting me here. Indeed, I will be talking today about mostly theory of planet formation, but there will be a lot of things about the solar system, because since I moved a year ago, as Condan said, to the Max Planck Institute for Solar System Research, I became much more integrated with cosmochemists, with people who study the also minor bodies in the solar system. So there will be some parts of my talk that will be about this. But for starters, let me show you something very trivial, something that all of you probably have seen, especially that in Graz the weather seems to be much better than in Göttingen, from what I noticed. So this is just a photo of an evening sky, just as you may see it with the naked eye. You don't need any telescope for that. And what you see here, despite light pollution, you can still see some stars. And what I want you to realize for the purpose of this talk is that most of the stars that you see on the night sky are thought to have at least one bound planet to them. And what we learned in the past 30 years or so of discovering these so-called exoplanets is that many of them are very different than what we know from the solar system. So sometimes you have historically the first known exoplanets, the ones that are super large but orbiting their central stars extremely close, so so-called hot Jupiters. And sometimes you may have systems that have multiple Earth-like planets, and they don't seem to have any giant planets at all. But most commonly, what we see in our galaxy now is something in between, so-called super Earth and mini Neptunes, so planets that we actually don't have in the solar system, so falling in between the Earth and Neptune. And of course, the question then that arises is how do all the planets form, and how is it possible that the process of planet formation leads to such diverse outcomes? And this is basically what I'm studying. And for now, we stay at the same part of the sky that I just showed. And some of you may recognize the constellation here, that is the Orion, is the most prominent constellation of the evening sky in our part of the world. And in the bottom part of Orion, there is an object that also many of you should know, is the Orion Nebula, very popular among astrophotographers. But if you are not just on Earth, and if you have some larger telescope, like the Hubble Space Telescope, you basically may keep zooming into the Orion Nebula, and you find that this is a region of active star formation, right? So what you can see there are basically individual objects which contain a very young star in the middle, that view of which is obscured by the dust. And it seems like these disks that are surrounding those stars are very dusty, but in fact, we know that the dust is only about 1% of the mass of this object. And the real question that the planet formation theory needs to answer is how do you go out of this 1% of micron-sized dust grains into the rocky cores of all these different types of planets? So all this journey from micron-sized dust to Earth-sized planet is already 13 orders of magnitude in size. And out of all these orders of magnitude, we unfortunately have only very limited observational access, right? So, of course, if you have the Hubble Space Telescope, you see the dust that is scattering the light. And then if you go to ALMA, of course, this is also a huge progress in our field that you can access the radiation from the larger dust grains. So kind of well-settled, what we think is the mid-plane pebbles, as we call them. And then in the future, we expect to extend to maybe centimeter wavelengths and then hopefully get access about the kind of largest grains, maybe answer the question like how large does the dust grain actually grow, but this is still not there. And then, of course, we see the end product of all the process in the form of all these exoplanets that I started with. So we know traditionally we detected all these planets that are very massive, very close, just because of the observational, so the detection bias is the easiest. And still, we kind of only have access to the part of parameter space that corresponds to either planets that are more massive than their equivalents in the solar system or closer in. And this is, of course, a big question where how well populated is the rest of this parameter space. And hopefully, also with the planet formation theory, we could answer this question. So it basically looks like we are missing this critical part of the planet formation process to which we don't really have observations. However, we actually do have some hints from our own solar system, right? So in the solar system, we have this population of so-called minor bodies, so the asteroids and the comets that are basically filling this region between 100 meters and maybe 1,000 kilometers, to which we have absolutely no access from the other systems. So the solar system, so the planet formation theory was actually heavily dominated by what we know about the solar system, just because we didn't know before, as the planet formation theory was developing, we didn't know about all the other exoplanets. And so just as a reminder, the solar system looks like this. We have the sun in the middle, then we have the 4 rocky or terrestrial type planets closer in, and then we have Jupiter and Saturn, and the 2 ice giants, Uranus and Neptune, farther out. And then all the space in between these planets, so every stable orbit seems to be filled with these minor bodies. So we have this asteroid belt that is very bright here because we know a lot of objects in there. And then we have the trans-Neptunian objects outside of the orbit of Neptune. But then also, if you look very closely, there are still dots here and there that are like populating all this space. And because of this observation, I think people kind of assumed that these asteroids and comets were the initial condition of planet formation, and the concepts such as minimum mass solar nebula and so on were developed, where people were trying to populate the disk around the young sun with such a kilometer-sized and larger objects and build their planets from there. This view is changing a lot, but still we think that these minor bodies may be a very good hint as a leftover from the formation of our own solar system. So we focus a little bit more now about what we learned from studying these minor objects. So we actually visited quite a few comets, and because for the asteroid belt, we kind of know that it is very conditionally evolved, so maybe these are not very good primordial planetesimals, but for the comets, it is not so sure. So there are, I think for very long, people would look at comets as these primordial leftovers and the original building blocks of planets. And now, if you look at this paper of Göttingen from this year, I think there are some dynamical arguments that every comet that is smaller than 10 kilometers is actually a fragment, or so it's a collisionally evolved. So maybe the best hint that we have from the formation would be that these trans-Neptunian objects, so the TNOs, and we visited one of them in 2019 with the New Horizons mission. And what you can see also in this gallery of the objects that we came kind of close to is that out of 7 objects, 5 of them are either bilobed, so like they have this actually 2 parts, or at least they are weirdly elongated. So they have this like interesting shapes. And people now think that this is actually telling us something about their formation process. And not only the fact that they are very often binary objects, but also their rotation. So in these trans-Neptunian belts, so far away in the solar system to which we rarely have direct access, but still we can study just by looking at the occultations of the stars that are even farther out, we can study the rotation of these objects. And the conclusion is that 80% of the trans-Neptunian objects show prograde rotation and about 20% retrograde rotation. And this is important because this fits extremely well with one of the scenarios that we have for the formation of these gravitationally bound building blocks of planets, so planetesimals, which is called the streaming instability, which I will show on the next slide. And why this is important? Because in the alternative scenario, if the dust keeps growing to larger and larger objects up to these kilometer and larger sizes, you would expect that these chaotic collisions lead to uniform distribution of the rotation. So that would be this thin line in the middle of the plot. While from the observations, we have this dark line, that is mostly prograde rotation. And then the solid line, solid black line that fits very well the observations is exactly the predictions from the model of the streaming instability. So what is the streaming instability? This is like something that was introduced in planet formation theory not even 20 years ago, actually. So it's fairly recent development. And the idea is that you take your micron-sized dust grains, you proceed with their growth by mutual collisions up to the stages of roughly pebbles. And the pebbles are important because they are characterized with their mobility. So with the possibility of disconnecting from the gas in the disk and drifting through the disk. But also it means that they can reach some higher densities, which is exactly what the streaming instability needs. So then we play this animation. What we see here is the density of pebbles. So this simulation is just started with pebbles. And then you see that these pebbles will form very overdense clumps. And if you look closely, some of these clumps are already rotating around each other. And this is exactly what the streaming instability models show, is that you have very high probability of forming binary planetesimals, and also that they will mostly have this prograde rotation. So from the perspective of someone who is working just on planet formation theory, the streaming instability is like offering you a possibility of jumping from the stage of pebbles to the stage of gravitationally bound kilometer-sized and larger planetesimals with no intermediate stages, which basically will mean that everything that you see in between would be collisional fragments formed from the collisions of these gravitationally bound planetesimals. And this is important because it solved a lot of problems that we had previously in the planet formation theory.
Quick question is, so is the actual force that clumps things together, what is it?
It is interaction between the gas, which is subkeplerian, right? So it's slightly rotating the star is slightly slower than the Keplerian velocity, which the dust doesn't really like. So because the dust would like to be on a Keplerian orbit. So what the dust is doing is basically equivalent to what the cyclists are doing in Tour de France, right? That they are kind of clumping together to fight the headwind from the Earth. So this is also
When you look at the movie, it looks like any galaxy is a simulation where
there is self-gravity that has to be switched on in these models if you actually want to follow the collapse phase. Well, like once you form, but here you just form the clumps, right? And then they would collapse to the final planetesimals, but the planetesimals would be so small that you would not see them, right, in this model. And also another aspect that seems to fit between the models of the streaming instability and the observations from the solar system is that because we are just like gently collapsing our clouds of pebbles, we predict that the comets formed this way will have a very low tensile strength. And this is, in fact, seems to be true. So we know both from the Rosetta mission that went to the comet Göttingen, but also earlier mission that was called Deep Impact. So this is the movie from this mission that actually impacted comet Tempel 1, is that the comets are very loosely bound. So basically what happened here is that this mission shoot a projectile into the comet, and this collision released so much fine material that the cameras were completely saturated. Also, this dust stayed around for very long, so it was impossible to see the crater that was made. Come back to this comet and actually take a photo of this crater years later. So yeah, it was a funny story that they wouldn't even predict how loosely bound this comet is. And still, studying comets remotely has a problem that we cannot really measure some interesting stuff. So, for example, from the Rosetta mission, we were not even able to exactly say what is the ice to refractory material ratio, which would be very interesting for people who study planet formation. So to measure these things directly, we would basically need sample. So that's why the sample return missions seem to be particularly valuable for the planet formation theory, but we don't have that many of them. So in the 70s, we had a lot of, so basically hundreds of kilograms of material returned from the moon, but then there was a very long break, and the only things that people were then collecting were single grams, so basically very tiny amounts of material. So the Stardust mission was from a comet of a short period comet GLS2, and then we have these three missions now that you might have heard in the news that were returning material from near-Earth asteroids, and each of the single sample return missions actually brought a lot of surprises with the analysis. So, for example, this one, the Stardust mission, there were some very refractory material, like similar to stuff that we see in meteorites found, that was not really expected in a very volatile rich comet. And then these three near-Earth asteroids, from remote studies, they look like there will be corresponding to parent bodies of also some known types of meteorites that we have on Earth, but a very detailed analysis still shows a lot of surprises that were connected to the fact that the meteorites actually pass through the atmosphere and have contact with things like Earth water and get processed, even if we pick them up very quickly after the fall. So it is absolutely invaluable if you have access to such fresh samples, and hopefully there will be more missions. I know that NASA is planning a sample return from a comet, maybe even 6070, which would be great because then we could compare all these remote observations that we have. So meteorites, I already mentioned. So you can, from the perspective of planet formation theory, You can look at meteorites as basically fragments of these primordial planetesimals, although this is already, of course, a huge simplification. And some basic facts about meteorites, since like I probably not everyone in the room is studying them, is that we have two major groups. One is meteorites coming from undifferentiated parent bodies, which we call chondrites, because you can see things like chondrules in them, which are very problematic and no one really understands how they form. And then you can also see these calcium aluminum rich inclusions, we call CAIs, which are the oldest solids that we have in the solar system, corresponding to the age basically of the sun, so 4.567 billion years. And then we have the other type of meteorites that are coming from differentiated parent bodies, which are either the fragments of the iron cores of these parent bodies, so the iron meteorites, or the fragments of the mantle, which we call chondrites. And then also another huge progress that we have is that in the recent years, the laboratory studies, especially the isotopic studies of meteorites, reached precision that is allowing them to measure differences in 1 part per million inside of in the material of this meteorite, corresponding to some specific isotopes. And what was found, was first published in 2011, is that we have something that is called NC-CC dichotomy, which basically means that any meteorite you pick up and you study the isotopic composition of will only fall in one of the two groups. And the red group is what we call non-carbonaceous parent bodies, and the blue group is what we call the carbonaceous parent bodies. And the interpretation of this fact is that there was some sort of a barrier in the early solar system that prevented mixing between these two materials. And so very often this barrier would be then associated to Jupiter. However, I always like to remark that we cannot be completely sure about how complete is this sampling by meteorites, because we don't get to choose from which parent bodies we get the meteorites, right? This is like luck and some collisions in the asteroid belt that bring the material on the collision course with Earth. And if we could, let's say, send a mission that would sample every single asteroid in the asteroid belt, would we get the same picture of dichotomy, or would we actually fill this parameter space more? I don't think we have any answer for this. But one very useful measurements that, or not direct measurements, but like study that we can do on meteorites is that we can learn about the timeline of their formation. So again, we have these two groups. We have in the red, the NC, which correspond actually to more volatile poor parent bodies, so not icy. That's why it's thought that they come from the inner part of the solar system. Also, Earth would be falling into the red category, which you could see on the previous slide. So the Earth, Mars, Moon are all here in this NC group. And in both of these groups, we have both these differentiated parent bodies and these undifferentiated parent bodies. However, there is some difference in the timing. So it seems that the bodies in the red group were forming for about 2.5 million years, while the bodies in the blue group, so more volatile rich, corresponding potentially to the outer solar system, kept forming even up to 4 or 5 million years. And all the times are measured actually with respect to the CAI formation. So that also is a relative timing, is not absolute time. Now we are coming to more specific results from my own work. Is that in 2018 I published a model for planetesimal formation. So I told you we now think planetesimals don't really grow out of collisions of dust, but you have the streaming instability phase, and the streaming instability phase means that you have a lot of pebbles in one place. And this was actually a big challenge. How do you put a lot of pebbles in one place? So how do you go out of a disk that has micron-sized dust that is very well mixed, and everywhere in the disk you only have about 1% of dust, to this condition for streaming instability that they need the dust-to-gas ratio of unity. So you need to increase your dust density by 2 orders of magnitude, at least. So I found in my research that it is possible, it's particularly effective around the water snowline. So this is this transition between ice existing as solid and ice existing as gas. And in this model, in particular, we actually start with forming our disk. So we don't have the disk at the beginning. So the snowline is very close in because the density of the disk is very low. But then as we build up our disk, the snowline moves outwards. So the x-axis here is the distance to the central star in astronomical units. So we basically go from something like 1.5 AU to outside of 10 AU. And this takes about 0.7 million years or so. And then we come back as the disk infall ends and the disk is entering, let's say, a normal evolution, just an accretion disk stage. And then the red color shows you how many planetesimals you form at each time. And then you can see that the planetesimal formation maybe doesn't happen everywhere in the disk, but it happens almost all the time. So you keep forming your planetesimals basically as long as the disk is alive. And then in the science paper that was led by Tim Lichtenberg in 2021, we have been able to show that this relatively simple model for forming planetesimals along the water snowline is roughly consistent with this meteoritic record of the solar system that I explained to you before. And the key here is taking into account the internal evolution of our planetesimals, which is mostly driven by their internal heating by the aluminum-26, so they're short-lived radionuclide with a half-life time of roughly 0.7 million years, so corresponding also to our disk build-up stage. So then the planetesimals that form early, they will inherit significant amounts of this aluminum-26, which will heat them up, leading to melting of the rocks and for forming iron core, but also loss of volatiles. So although all my planetesimals form along the water snowline, so they are basically relatively water rich, the ones that form early will completely lose the water. And then, of course, the ones that form later, also more in the outer disk, they will not experience such amount of processing, and they will then stay as parent bodies of this undifferentiated, so these contracts. But of course, this is still not the end of the story, because this is not planet formation model per se. We don't form any planets, right? So this is only a model that includes the dust growth from micron sizes to pebbles, and uses the string instability predictions to tell in which places, so where and when would you turn your pebbles into planetesimals. And you might have heard that for the actual planet formation, the current dominant paradigm is so-called pebble accretion. I think that you hosted also a seminar by Anders Johansson, so he probably have told you more about this. So in this classical planet formation theory that was like starting with asteroids and comets, the problem was that the growth of a protoplanet was not very efficient, because the gravitational interaction between this protoplanet and kilometer-sized planetesimal was very often leading to scattering. So even if you managed to bring your planetesimals close in to the protoplanet, it would just get away, and it would not really contribute to the growth of the planet. But with the pebbles, the story is quite different, because they are still interacting with the gas. So all of this and this interaction is on the time scale that is just right, such that the pebble will get slowed down close to the planetary core, and it will get accreted from a region that is much larger than just the geometric cross section, right? So this is the big advantage of pebble accretion, is that you can kind of sweep up your pebbles from larger portion of the disk. And also we are now shifting the mindset from a disk filled with planetesimals to a disk in which planetesimal formation is rather rare, and you just put your planet in a sea of pebbles. And this is indeed how the current planet formation models work. So this is an example from the 57 chapter, actually, that Kundan mentioned. It's a figure made by Bertrand, who is also one of the leading experts in this pebble accretion world. So the pebble accretion models work like this, that you start with a relatively massive protoplanet, so typically something like a moon mass that you already have to insert in your initial condition into a disk of pebbles, and then you may regulate how many pebbles you have. For example, if you connect the amount of dust in your disk to the metallicity of the central star, and then you basically let your moon mass planet grow by accreting these pebbles, and also at some point it will start migrating in the process that is like just gravitational interaction between your protoplanet and the surrounding disk, so the gas disk, that causes the planet to move. And the big advantage here is that you can actually produce a diversity of outcomes that is roughly corresponding to the exoplanets that we observe. So depending of where and when you insert your protoplanet and how many pebbles you have in your disk, you can end up with either Jupiter or Saturn, or you may end up with hot Jupiter, or you may end up with close-in super Earth, right? So it just depends on your parameters. But yeah, of course, it's a big question of how do you know these parameters. And let's see. Yeah, so indeed, this paradigm has a lot of success in reproducing what we observe in the exoplanets. So this is results that were published in a paper led by Heismulders in 2021, which his aim was to explain very puzzling correlations that we see in the exoplanets occurrence rate as a function of the host star mass. So it was known as one of the results from the Kepler mission was that the less massive host stars have more close-in planets. But the results from some long-running radial velocity surveys are the opposite, that the more massive the star, the more of cold giants you get. So the scenario that we proposed to explain it with pebble accretion was that more massive stars more often will have high mass disks. And high mass disks have a higher possibility of forming a very massive planet. We know that to accrete gas, you have to be farther away from your star because it's easier to accrete cold gas than is to accrete warm gas close in. So in summary, the high mass disk will have a higher chance of forming a Jupiter, and then this Jupiter will block the influx of pebble into the inner disk, which will result with a lower probability of forming a massive detectable close-in planet. You can still form Earths, but we cannot detect Earth, right? And then the low mass host stars will have lower mass disks that will fail at forming a massive planetary core quickly enough to accrete a lot of gas, but will still then be able to pass these pebbles to the inner disk and grow close-in super Earths or mini Neptunes that we could detect. And this all was done using a very simple so-called pebble predictor, which is just a Python script that I put up publicly on my GitHub, that you can use to predict the fluxes and the sizes of your pebbles in accordance to what we understand about dust coagulation. But still, there is something missing again in this model, and this is the substructures. So in all the models that I showed you before, we assume that the disks are perfectly smooth, that there is nothing interfering with the flux of pebbles as they are moving through the disk. And we know that this is most likely not true. So most of the disks that we were able to resolve show so-called substructure, which may be in the form of these rings and gaps, sometimes more like galaxies again, so spirals, sometimes non-axisymmetric features such potentially vortices and so on that are collecting pebbles only on one side of the disk. And this is also became a huge topic in the planet formation theory. What do substructures do to planet formation? And we have also studied that in the group in Munich where I did my postdoc. And our conclusion is that they actually help. So basically, from a perspective of planet formation theorists, substructures or like a ring would be a pressure bump. Pressure bump, again, I mentioned before the subcapillarian disk. Pressure bump decreases how subcapillarian the disk is, which basically means that for dust, the dust doesn't have to fight with this headwind from the gas so much, and this makes the dust preferentially concentrated in this region of a lower pressure gradient. So this the plot that you see on this slide is coming from another publicly available code, which is called DustPy, which was developed by Sebastian Stammer and Phil Winston in Munich. And this is a 1D code. So you basically have just a distance from the central star. So you assume that the disk is axisymmetric, and you assume that it has some well-known vertical structure in equilibrium, but you solve for the coagulation of dust. So the colors show you how much density of dust you have at each radial distance and corresponding to each mass of the dust grain, right? So again, you start with 10 to minus 12 gram, which means basically 1 micron dust, roughly, and then you go up. And this kind of bright ring that you see here, this is also what you would see as a ring in this ALMA observation. So what we found is that in a pressure trap, the enhanced dust density will help you to trigger the streaming instability, but also it will help you then to have very efficient pebble accretion because you have a lot of pebbles in one place. And the pebble accretion is actually even more efficient because of these headwinds that slow down. And also, very importantly, the planetary cores are safe from planet migration because it's such a pressure bump would also correspond to migration tracks. So you will not have the problem that once you grow to roughly 10 Earth masses, you very quickly move into your disk. And then these are results from a project led by Tommy Lau, his PhD student at LMU, and that we already published last year, where he stitched together two codes. So this was something that was really missing in planet formation model, that either you dealt with the growth of dust grains or you dealt with like what happens after you have your moon mass planetary core, but there was no codes that were investigating this in between region. And this is finally what we have been able to do thanks to the work of Tommy. So the bottom panel will be again our DustPy results, and the top panel will be results from n-body code that is coupled to this DustPy. And then we also have our pressure bump here. So we collect our dust, and then as it collects, you trigger streaming instability, you produce your planetesimals, and then these planetesimals very quickly grow, mostly by pebble accretion, into planets of a couple Earth masses. And then what is interesting is that the planetesimals that form first, because all these timescales are competing, so the planetesimals that form first, they don't wait for the next planetesimals to form, they already grow by pebble accretion, And this means that they also scatter each new planetesimal that comes, cannot grow because it will be put on some very eccentric orbit by scattering and will be less you get out of one pressure bump or one substructure. And now coming back to meteorites, because coincidentally, we also found that, or not really me, so this is a work that was led by Jan Hellman, who was working with the group that I am now collaborating in Göttingen. So this is the group that studies isotopic composition of meteorites. Here in particular, we only focus on meteorites, so the one in the blue group from the outside of Jupiter potentially. So in these carbonaceous chondrites, you see you can kind of simplify it to three components. One is the CAIs, the oldest solids that I mentioned at the beginning. Second is the chondrules, so these puzzling droplets of molten rock that solidified and is now incorporated in the meteorites. And the matrix, which is what binds them together, what fills the rest of the space. And you also see signatures of each of these components in this isotopic composition. And what was the result from this work was that the abundance of chondrules and CIs is correlated, so it's not independent. So basically, I can see the CI, which basically means matrix, the chondrules on this edge, and the CIs are somewhere very far away outside of this plot. And you see that these dots corresponding to different meteorites are not filling this space uniformly, but are like correlated, right? And to make it even better, it also correlates with the age of the parent bodies. So basically, the meteorite parent bodies that formed earlier have more CAIs and chondrules, and the ones that form later have more matrix. So basically, these CI Ivuna-types chondrites are just matrix. They don't have any CAIs and chondrules. And we interpret, or we actually propose interpretation of this observation as a formation of these parent bodies from a pressure bump, or maybe multiple pressure bumps, we don't know yet. And that would basically mean that the CAIs and chondrules are preferentially incorporated by the string instability, which is also predicted in the string instability models that the largest or highest, densest, so highest Stokes number, as we say, grains are preferentially incorporated into these filaments and the clamps. And then the matrix dust would only be incorporated if you already ate up all of these kind of heavy components. So we now hire a PhD student to exactly check in actual models if this interpretation is correct. And then I'm actually at the end of my talk now, so this is the last result that I want to show you, is from a paper that is currently under review, where we extended the model that I showed you before about stitching together dust pile and n-body core to model all the planet formation stages at once to gas accretion. So now the previous model ended when the planetary core had roughly 4 Earth masses. Now we don't end the model, we actually let it go and the planet may accrete gas. So again, we have some initial substructure that forms our first burst of planetesimals. And this first burst of planetesimals quickly forms one and then the second planetary core that is able to start accreting gas. And the gas you can then see as this like greenish envelope. And as the gas accretion happens, also the planets interact with the gas. So the gas is the bottom panel and open gap in this gas that influences the accretion of pebbles. So this is all connected, right? And then the region of the pebble accumulation is then shifted outwards as this process goes and triggers another burst of planetesimal formation. And then out of the second burst of planetesimal formation was actually third burst because there was one in the middle that we didn't really see well here. And there are another 2 planetary cores formed. But since they formed almost 2 million years later, when some part, significant portion of the gas and pebbles was already gone from this disk, they won't be able to grow to Jupiter and Saturn, but they will stay more like at this ice giant sizes. So you understand that. So it seems like we have a model that is pretty robustly explaining formation of a sequence of massive planets, such as Jupiter, Saturn, Uranus, and Neptune in the solar system, and potentially some of the exoplanet systems. And we found also we couldn't really afford to do like a full parameter study because this numerical method is still pretty expensive and it takes like weeks to accomplish one run. But we found that by just varying for things like, for example, the background turbulence in the disk a little bit, we can completely change the outcome. So we may, for example, only have one planet forming, and then the rest is not able to form more planets, but we may also form, like we may play with the time scale of this burst of planetesimal formation. So we expect that like with varying more parameters, you can kind of get a different planetary systems out of the same basic scenario, which is exactly what we are looking for in planet formation theory, right? Okay, so this is the end. These are my couple of takeaway messages. So things that we basically have a huge progress because we discovered these different exoplanets. We were able to look inside of these circumstellar disks, and we now also have laboratory studies of the solar system that tells us very particular details about how our own solar systems form, that we may kind of try to get hints about general planet formation process. I mentioned things that are like keywords in the current planet formation theory, like the pebble accretion, also the streaming instability, and that we now think that the initial disk is not filled with planetesimals, but it's more like you have some isolated places where you form planetesimals and the rest stays as pebbles. And the last result is that if you connect everything together, all these stages together, you may get something like this sequential formation of massive planets that may potentially explain the outer planets of the solar system. So yeah, if you have questions later, you can always email me or find me on X, that sounds very weird, or Blue Sky, and yeah, looking forward for your questions.
Any questions? Maybe let's start with Siak.
Oh no. So if you form planets via pebble accretion, it's my understanding that you tend to need quite a lot of.
No, you don't need it.
Okay, just
Yeah, the microphone should pick it up.
All right. I mean, if you guys can hear it also. So if you form planets via pebble accretion, it's my understanding that you need quite a lot of pebbles, and in general, you need quite large, massive outer disks.
This is true if the disk is smooth. So this is exactly why the substructure helps so much, right? Because you kind of recycle your pebbles because you keep them in the same place. So you, in the classical model, indeed, to grow to one Earth mass, you need roughly 100 Earth masses in pebbles, which is completely inconsistent with the observations, as you probably know. But in this scenario in which we have substructure, you don't need as much. So you actually, I think Tommy checked that, it was something like 90%, 80-90% of the efficiency in how many pebbles you had in your outer disk and what went inside of the planets.
In that case, can I ask the opposite question that I was going to ask? Because that was indeed my concern. It's like basically, can you then go from the observed planet population to the observed size distribution that you would need? In that case, can I invert it and say, can you already get, considering we have a bit of an idea of what the distribution of substructures and disks is like from something like D-sharp, can you sort of invert that and say, well, then that gives you this efficiency for planet formation?
Yeah, I think that in general, this is roughly consistent. So I think the like average disk masses in pebbles are roughly what you see in the outcome in the exoplanets. However, the spacing is different. So this is also there is a figure about this in the 57 chapter that Scheidel just did, where he showed that basically the disk has just the right mass, but they have it too far away. So you still have to like transport either by the pebble drift or by the planet migration or both, most likely both. You transfer the mass from the outer disk into the more compact planetary systems.
Thank you.
Maybe
Before we know, there are now some JWST observations of protoplanetary disks of low mass stars like M5 or so. So I think we have two objects now which show very surprising features. I mean, namely that the innermost inner disk seems to be carbon. So we tried that with our models, and there's no waterline emission. We see a lot of hydrocarbon molecules, and even there's no CO, but very little CO. So the only way to reproduce this is to assume that you have something like, so the oxygen is basically gone. You need C over O like 1,000 or so, but not so much carbon enrichment, but rather oxygen depletion. Now, from your models of pebble drift, etc., and water lines, so evaporation. How do you interpret this? Do you see a way to understand this?
Yeah, honestly not. So I think you would have to bind all your oxygen in planetesimals or planets, right? To not allow it to go into the inner disk, which may be done if there was some substructures indeed, but you still like need to have carbon. I think from what I understand, the carbon you can get from, for example, destroying like organic grains by various processes, by temperature basically, or by UV radiation and so on. So yeah, I think that would need to be some sort of combination.
So one of the ideas that you actually somehow capture or stop the migration of all these pebbles which have the oxygen in form of water, but the gas is carbon.
Yeah.
And now, but then you need to kind of assume that the gas continues to get accreted towards the star, but you held back.
I think this in general is possible. So gas, it is hard to hold the gas completely, right? Because it will always have some viscosity. So even if there are substructures, the gas is intended for flowing. Even if there is a planet, the gas is still flowing through the planetary gap. The pebbles may be blocked. But
because what the community seems to discuss now is often just so head wavy. So we have these pebbles and they are trapped and then in this room, but there are no models for this.
I think we are now like, exactly at the stage in which we finally have some sort of self-consistent models, right? But still, the price of being self-consistent is that it's so heavy that we have to put the inner edge is at 3 AU, right? Because we need to reduce the computational cost of solving the inner solar system. Yeah, so there is still something to do.
I have two questions which I will try to stitch together. The first one is in your plot where the snow line is moving in the beginning, in the build-up phase. Could you explain what is the build-up phase and why is the lane? So it seems that the temperature rises over time.
Yes.
And this brings me to my second question, which is what is the starting point for your simulations? Because in the plot that you stitch the two models, it seems that it's like a flat population start to grow. Is it the build-up phase? Is it after? Where is it in this plot that you start simulating?
It's a very good question. So you basically notice these are two different models, right? So in this model, our initial condition is molecular cloud. Molecular cloud of gas and dust, like sphere of Earth, homogeneous density, and some solid body-like rotation. So not very realistic, but that's what we get. No, in 1D model, that's what we can put. And then you basically just put in the conservation of angular momentum to check which portion of the molecular cloud is falling to form the star directly and which portion is falling to form the disk. And then the disk grows from inside out. So we sometimes say this is inside out disk infall model in which you start with a very tiny disk. So basically you build your inner part of the disk first, and then That's why the snow line cannot be anywhere else because there is no disk at 3 AU yet, right? So basically, that's the result. That's the reason for this. You build very compact disk at the beginning, and then the disk is growing by the continuous inflow that with time extends, but also the disk is spreading because if you build very compact disk, it will be spreading just by viscosity.
So the temperature increases just because the disk extends.
Yeah, exactly. And the temperature, you have two sources. For temperature, you have the irradiation from the central star, and you have the accretion heating. So the fact that it's accretion disk, right, and then just the accretion flow will produce some heat. And this is mostly the accretion heating is important in the inner part of the disk, especially if it's dense and turbulent, and the irradiation is important in the outer parts of the disk.
It goes very far, to 15.
Very far, exactly, indeed. So this is because in the most massive, so in this point, right, where the snow line cuts, the mass of the disk is 20% of the solar mass. It's a very massive disk at this stage.
Question?
Yes, it was partially answered in the previous answer, but in continuation, so if you take into account the momentum conservational aspects, can you also interpret the fact that, for example, in the solar system, our giants are relatively fast rotators, and how fast are rotating your exoplanets? And additionally, we also know quite a strange behavior of the outer planets, Uranus, specifically very special rotator. And in that sense, what are the limitations and what are the capacity of
a question, but it's like, yeah, of course, our models don't have rotation of the planets or anything like, or even planetesimals or anything like this. But I think in the solar system, like what we have is an effect of what happened after the stage that I modeled. So here, if you look at this movie, what we end up is a very compact configuration of Jupiter, Saturn, Uranus, and Neptune. So basically, the Neptune, I think, is something at 17 AU, while today Neptune is at 40 AU. And there is a stage in between that happens after the gas disperses completely, which we don't model, which is called the Nis instability, which basically means that these planets go through a period of like very dramatic instability. That there was a paper about this 20 years ago, I think. I think if you Google it, it's on Wikipedia. It's the Nis instability idea basically explains a lot of features in the solar system, including this spacing of the planets. Why Neptune is so far away? It's very hard to form a planet at 40 AU. So we form them much closer in. And then the idea is that they then go through a period of gravitational instability because they are actually too close and the gas is damping their mutual eccentricities and so on. And then they space out. Neptune lands at 40 AU. Does it explain the tilt of Uranus? I'm not sure. I've seen explanations that require some giant impact, basically.
Probably Uranus is a unique case, but
So tilted, yeah.
When you say it's very hard to form a planet at 40 AU, it depends on the size of the disk, right?
Not only so.
Or the starting point of the disk.
Yeah.
But my question is, we observed disks with ALMA and so on, right? Have we observed formation that far, or at least gap in the rings that far?
Yeah, we even have exoplanet systems that have planets at 100 AU. So you have, for example, this famous PDS-70 that has two planets that are more massive than Jupiter that are farther out than Neptune. Or something about this. So it is definitely possible. However, the problem are timescales. So just like if you look at the Keplerian timescales, right, they are increasing drastically as you go outward, farther out from the sun. And then all of these physical processes that I'm talking about, like dust coagulation, pebble accretion, everything gets slower if you go farther out. So the lifetime of the disk that is like maybe 3, maybe 5 million years may not be enough to form anything at 100 AU or even at 40 AU. So this is the real problem.
So let's take last question.
Yeah. I have a very beginner question. So in your model, so in your self-contained consistent model, everything occurs in the single disk. But is there any possibility that the other condition may play some role? For example, is there any chance that interstellar matter interact with the formation, or there could be other possibility, rendezvous with other stars?
Yeah, I think what you are talking about is also touching a subject that is very quickly developing in the planet formation, and this is this idea of so-called late infall. So basically that your disk is never finished, that you can always add some material because your protoplanetary disk will be encountering some cloud of interstellar material. I honestly don't really have an opinion whether it played a role in the solar system or not. It would be definitely very convenient to explain some very volatile rich, for example, bodies, because in these models that I showed with the infall, everything falls at some point relatively close to the sun, which would mean it's processed, which is not very consistent with the fact that in some comets you see some very volatile material that was probably never heated past Atlantic earlier. But yeah, I don't really have any models. So this is also something that I really want to work on in the future.
So, thanks, speaker again.